I started with this image up here on the screen of Florida, where you can see the present-day coastline, and this kind of outlines the talk a little bit, but you can also see a past coastline and perhaps a future one as well. So out here, way off in what's the Gulf now, right, and then on the Atlantic on this side, you see what's labeled as the Ice Age shoreline. So during the last Ice Age, about 20,000 years ago, there were mastodons roaming across Florida. If you've ever been to the Florida Museum of Natural History in Gainesville, you might have seen some of those skeletons there, right? And the reason that Florida Peninsula was much wider then is because all of that water, it was in the oceans, a lot of it was trapped up in those ice sheets. Then as the ice sheets melted, that filled the ocean's basins and sea level rose to its present position here, right? And the reason it's so much wider on the Gulf side, in case you're wondering, is because the gradient or the bathymetry has a very shallow angle on the Gulf of Mexico, right? So a small vertical change in sea level translates to a very large coastal retreat. So that bathymetry or topography is really important in determining when sea level rises how much it actually retreats inland, right? So it turns out that you're better luck on this side of the state than the other side for that reason. All right, so the other thing that you can see labeled here is in fact another past shoreline in the black, right? This comes from a time period that I'm going to be talking about that I study a lot. It's called the last interglacial, right? So before the last ice age, which we refer to as a glacial period, there was another warm period, so we call it interglacial. It becomes between the ice ages, right? And that was about 125,000 years ago. And all across South Florida here, there are shallow marine deposits, right? There are things, little balls of carbonate called ooids, which make my favorite rock ever. My favorite rock is an oolite. And you can see ooids forming today on the Bahamas banks. So it was an environment something like that 125,000 years ago down here in this part of Florida, right? So sea level has changed in the past. And as geologists, we can kind of study the dynamics of that change in sea level and ice sheets and climate to understand how that system works. And that helps us then to project what is going to happen in our future. Well, the reason for sea level changing on these timescales had to do with changes in how much of the sun's energy was coming into planet Earth. But today what we are doing is we're pumping a lot of greenhouse gases into the atmosphere, and that is what is warming up our planet. So the sea level rise that we see today is in fact quite rapid compared to anything we've seen in many thousands of years, right? Because after the last ice age, when those ice sheets disappeared, sea level stabilized, right? And humans colonized the coastlines and started building structures, and it was fairly stable. And all of a sudden, we put all these greenhouse gases into the atmosphere, and we've ramped things up, and it's now changing very quickly again. And instead of showing you a graph of what temperature looks like, I much prefer this color scale that you can see across the top of the slide here, and you might see it throughout the talk. That color scale shows you temperature on a color scale from the year 1870 to 2017 on the right. And what is especially great about it, it's very visual, very impactful. There's no question you can see this very rapid change in temperature when you get over to the right-hand side. But it's also portable. Look at this, right? So your next dinner party, right, you can take your scarf and show people this is how temperature has changed. And this is what we have done to the planet. All right, so to start off, I want to give you a little bit of an idea of what it is that I do as a geologist, right? So I'm going to show you a quick 2-minute video of me in the field so you can get an idea of this. Sometimes people think of the work I do as trying to save the planet. I'm not really concerned about the planet. I'm a geologist, and the planet has been here about 4.5 billion years. The planet's going to survive sea level rise. It's still going to be here. The question is, though, how are we going to survive? And one of the things we need to know in order to prepare is how quickly is this process going to unfold? And one way we can answer that question is by looking at Earth's past. because to some extent, the Earth has done this experiment for us before. We're looking at this by studying fossil coral reefs. Corals grow near the sea surface because they need the sunlight to survive, and so we use them to track the position of sea level in the past. Coming to the University of Florida was a really natural choice for me. It's a collaborative environment within departments, within the college, between different colleges in the university, and all those things have a great appeal. We're building an incredible depth of knowledge about what's happening to our planet. And one of the things that we can do is use this information to help us to create a new future. A future that we want to be a part of. Go greater, go Gators, right? So that, obviously there was a little bit of branding that went on in that video. They made that for their fundraising campaign, so that's obviously supposed to make you want to reach into your pocket, right? But that's not why I showed it to you. The reason I showed it to you is because, first of all, you really get to see what it is that I do out there. And the second reason is because it also shares with you a little bit of my philosophy about why it's so important, right? People talk about saving the planet or saving the polar bears, or you might see pictures of ice sheets when you hear people talk about climate change. But really, the reason that this issue is so important is because humans are at the center of it, right? The reason it's important is because we're concerned about how we are going to continue to exist within this very rapidly changing climate, right? The Earth is still going to be here, albeit it might be a very different place, right? But what makes this important is how humans fit into this picture. So I wanted to start off with a little bit of the context of what's driving sea level in terms of the climate change that we're looking today, because there's a lot of confusing information out there in the media right now and that you might hear on the news. And so we're just going to run through a little bit of this very quickly so that you have this background before we talk more about sea level rise. So I often get a question, or you also hear people say, and some of our politicians in the state have said this recently, in fact, they say, well, we agree, global warming is happening. It's gotten to the point where you really can't deny that it's happening anymore. But we really don't know how much of it is due to humans, right? So asking this question, it pains me so much to write this that I had to put the answer right here underneath it in the subtitle, right? So it turns out we actually do know the answer to this question. And it's not even just like a little bit of the warming is due to us. It turns out that all of this recent warming is due to us, as I'm going to show you in a moment. And as a geologist, one of the things I do is I'm a chemist, I'm a geochemist, and we can look for chemical clues in the rocks, like fingerprints. So I'm kind of like a CSI, right? Crime scene investigator, planet Earth, right? They haven't made that one yet, but you know, maybe they will eventually. So that's what I do, and I go look for clues of what happens. And it turns out that this case was a really easy one for us to crack, because everywhere we look, carbon dioxide has its fingerprints all over, right? So what I like to say is that carbon dioxide is kind of like the world's dumbest criminal, right? It leaves its evidence all over the place. Everywhere we look, we can see evidence that that's what's responsible for the warming that we see today, right? So instead of a graphic, I'm not only going to show you a few graphs tonight, but I couldn't resist putting these ones up because this shows you how much of it is due to us. So if you look at the black line, again, going from about 1870 to present day, this shows you global average temperature change over that time scale. That's that color scale that we were looking at before. And then in blue, when we use climate models to try to reproduce this trend back in time, if we only look at natural factors, like how much of the sun's energy is coming to Earth and how that changes through time, then it looks very flat. We just cannot reproduce this rapid uptick in temperatures at all if we only look at the natural factors. But if we add in human factors, right, and specifically only when we add in the greenhouse gases, we are able to reproduce this trend with the climate models. right? In fact, this factor here, which is called aerosols, that doesn't refer to hairspray, by the way. Aerosol is a small particle in the atmosphere, right? So pollution that we put into the atmosphere actually reflects some of sun's energy back into space. It has a cooling effect, right? So that pollution has actually been slightly cooling the Earth. But we have overcome that cooling and then warmed on top of it, which is why I say that all of this warming is really due to us, because we even overcame it should be slightly cooling because of that pollution trend, right? So whether we look at the evidence in the rocks or we use the climate models, it's convincing that global warming is in fact due to us. You might think that's depressing. I think that's good news, right? Imagine, what if it wasn't us? What if the Earth was moving towards the sun really quickly, right? What were we going to do about that, right? That's not an easy solution. But because we are the problem, we can also be the solution, right? And we can take control of that. So I actually think that's a very positive result. Okay, so the other thing that you might hear sometimes is, oh, well, this is just part of a natural cycle, right? As if a geologist has never thought about natural cycles before, right? So let me show you what natural cycles look like, because they do exist. Some of my colleagues go to ice sheets to do their fieldwork. You saw I get to go to nice places where I drill coral reefs, right? Tropical islands, which is not a bad gig, let me tell you. But some of my friends end up going to the ice sheets to look for records of past climate change. And what they're holding here is a sliver of an ice core, and hopefully you can make out there are little air bubbles in that piece of ice. And they can actually measure the composition of the atmosphere back in time as it's recorded in this ice core. And you can see natural cycles. I think you can all see these cycles in the concentration of carbon dioxide in the atmosphere, the concentration of methane, another greenhouse gas, and we see natural cycles in temperature. And this is going over 800,000 years from left to right, where present is on the right side of this graph. But today, these spikes that you can barely see because they go straight up, we're now at about 411 parts per million of carbon dioxide, way up, completely off the scale, right? And methane as well. This is very clearly not part of a natural cycle, right? We are way outside of the window of what we've seen during any of this time frame before. And yes, 400 parts per million sounds very small. And sometimes I get the question of, well, it's so small, how can that really have a big effect, right? Well, if one of you had a glass of water and I just put, I don't know, one little drop of arsenic in it, it might have a really big effect on your life, right? So small things can sometimes have very large impacts, and that's not to be overlooked. All right, so that sets the scene for what I really want to talk to you about tonight, which is sea level rise. Because as the planet is warming, the oceans are rising for two primary reasons, right? One is that as the water heats up, it expands. And secondly, because we're melting ice that's sitting on land at the same time. So this graph right here shows you since 1993 to present, we've had satellites up orbiting the globe to get a very good picture across all of the oceans to see what's happening with sea level, right? And so over those few decades, you can see sea level is very steadily marching up, right? At the rapid rate of 3 millimeters per year. It doesn't sound very impressive, does it? 3 millimeters a year. I mean, that's the thickness of 2 pennies stacked together. So I'm looking out at this audience. I'm guessing a lot of you have coastal property, right? And you might be snickering off the back saying, 3 millimeters a year, right? Like, I'm good, right? Why in the world do I need to worry about 3 millimeters a year, right? Well, it turns out that in the context of the last several thousand years, 3 millimeters a year is actually very fast. And it has pushed our coastlines out of equilibrium with the position of sea level. So let's look a little farther back in time to put that 3 millimeters a year into context. This graph is now showing you from the year 1900 to present. And there are 3 different lines drawn on here. Those come from 3 different research groups who are working independently. They were all using the same data set, looking at tide gauge data from the last century. And the reason they disagree back here is there weren't very many tide gauges in 1910. So it's very hard to interpolate what the global average is. But regardless of which one of these you look at, there's no question that it's been rising and that it's been accelerating over this time frame. But the rate of rise in here, if you average it out for any one of these curves, is only about 1 to 2 millimeters a year. And now it's actually almost 4. I put 3 point something on the last slide. It's actually closer to 4 now. So this acceleration, it turns out, is due to an increasing contribution of meltwater from the Greenland ice sheet and from the Antarctic ice sheet, right? People used to think that those are such large ice sheets, it would be really hard for us to perturb them enough to get them to start to melt quickly. It turns out we've woken up those sleeping giants, and that even with the amount of temperature change that we've already seen, that this meltwater has been accelerating, and that is in large part what's driving the acceleration in sea level that we see today. Okay, so 3 millimeters a year is fast within the context of this, but still you might think your beach house is good, right? Well, let's see what 3 millimeters a year does. This is a barrier island, much like the one that we're standing on now, right? Except this one's in New Jersey. This is Long Beach Island, and you can see up here where people have built on it, they want it to stay in the same place, right? Like many of the houses in this research lab, we don't want this barrier island to move because we've built on it. The only reason there's a beach out front here is they've been renourishing this beach, right? Because what happens during the storms, as I'm sure many of you know, is that the waves pick up the sand and they wash it over to the backside of the barrier island. And as sea level rises, that barrier island wants to retreat landwards. It's just washing the sand back, kind of rolls over on itself backwards. Geologists are creative people. We call these washover deposits, right? And that's exactly what you're looking at here. So you can see what 3 millimeters a year has already been doing, right, to this barrier island in terms of retreat. So this part of the coastline is already out of equilibrium with where sea level is. And so it's no wonder that when you get storms coming through like Hurricane Sandy, that's what Long Beach Island looks like, right? So yes, 3 millimeters a year is something that we need to be worried about. Okay, so the big question, and the reason that you probably all came here tonight, is you want me to tell you how much the sea level is going to rise and how fast, right? Those are the two big questions. So to do that, that's basically the focus of my research. Instead of thinking about the future, I'm going to look into the past. Because as you saw in that video, the Earth has been warmer in the past, and we can look at that example to understand how did Antarctica and Greenland respond to that? How high did sea level rise and how fast did that happen? And that can give us some better constraints on the models that we use to project sea level rise into the future, right? So what I do is I look at these past time periods to understand how these ice sheets responded. And as you saw in the video, I get to travel all over the world to tropical islands and drill into these fossil coral reefs. Corals live near the sea surface because they need that light to survive, right? And we use those to track the position of sea level through time. So I'm going to show you some of the results that we have from this work that we've been doing all around the world. And there was a paper that we wrote a couple years ago with a whole number of people, and they weren't all people like me. Some of them were ice sheet modelers, climate modelers, people who are all looking at this question from different angles. So we decided to write a review paper, say, these are the things we understand, and here are the things we don't understand, right? And this is what we need to focus on as we move forward. So I'm going to show you the summary diagram that came out of that paper. So what you're looking at here, we looked at 3 past warm periods, the warmest ones in the last 3 million years. That's this last interglacial time period that I mentioned to you before. That was about 125,000 years ago. There's another one here 400,000 years ago and one 3 million years ago. And this is today on the left. So here's sea level at 0 by definition for today, and this is the configuration of those 2 ice sheets at the poles. What we have done is we've ramped up carbon dioxide in the atmosphere very quickly, and that's had the effect of raising temperature by 1 degree Celsius, which again, doesn't sound like a lot. What I didn't tell you on that first slide when we were talking about the last ice age is that it was only 4 degrees Celsius colder during the last ice age, and we had ice sheets more than a mile thick. So these small changes in temperature, when you're talking about a global average temperature, it has an enormous effect on the globe's climate. Right, so we've already increased our temperature by that much. So we looked at these past warm periods where we warmed up the Earth anywhere from 1 to 3 degrees Celsius warmer than pre-industrial. And we saw repeatedly that sea level rose by at least 6 meters or more So for context, 6 meters is about 20 feet, right? 9 meters is about 30 feet. So we're talking at least 20 to 30 feet of sea level rise, enough to 30 feet probably just about fill the room to this ceiling, on average. Some places would have seen more, some places would have seen a little bit less, right? That's really a sobering result, right? So that main takeaway from that paper is that these small, what sound like small increases in global temperature, right, and just a few degrees of warming at the poles, we can get a very large response from those polar ice sheets, right? Okay, that's the depressing part of the talk. We got that out of the way, right? There's good news and bad news here. That was the bad news. The bad news is that what we've done is we have warmed up the Earth. What I like to think about, it's like warming up a room and taking 2 ice cubes and throwing them in and sitting back and watching what's happening. And that's basically what we're doing now with these ice sheets. We're watching. How are they going to respond to this large increase in temperature? Because now they are out of equilibrium with the climate that we have put them into. So this is what 6 meters of sea level rise would look like over the state of Florida. And over here, for reference, that's what New York City would look like with 6 meters of sea level rise. All right, so that's the bad part. Here's the good news. This will not happen overnight, and probably not in our lifetimes, right? We are not going to see 6 meters of sea level rise. But that clearly begs the question of, okay, but when, right? How fast is this going to happen? And is it going to be a gradual rise up? Or are we going to have a sudden collapse of a sector of an ice sheet and we're going to get a rapid jump in sea level? Like, are we going to go up like a staircase, right? Or are we going to go up? That's a really important question that we're trying to answer because that has huge impact on how you're going to plan for this, right, in terms of coastal planning. Right, so that's the main focus of my research now is to try to understand the rate of this rise and the dynamics, right? Will it happen gradually or rapidly? That's a question we still don't have the full answer to because we don't completely understand the physics of this ice sheet retreat, and that's the largest uncertainty in the models that we're using right now. But when we look at this past warm period that I've been studying, the last interglacial, 125,000 years ago when sea level was 6 to 9 meters higher, right? To get that high, we would have had to tap into ice at both of the poles, right? The reason we know this is we can heat up the water a little bit. We could melt all of the mountain glaciers on Earth, and if you add those 2 things together, you would only get about 1 meter of sea level rise, right? Now, we know during this time period that part of the Greenland ice sheet did not melt because we have ice cores through it, and there's ice from that age, so we know that it didn't melt away, right? So most of the northern part of the Greenland ice sheet was intact, but the southern part melted, and it probably contributed about 2 meters worth of sea level rise when it averaged around the globe. So to get anything more than 3 meters, these 2 things added together, we really have to tap into the Antarctic ice sheet, right? So that's why this result of at least 6 meters is very important. People are quite worried about the Antarctic ice sheet. It's something you may have heard a lot about the news. You probably see pictures of ice shelves breaking off all the time. The reason that they're worried about the Antarctic ice sheet is because large parts of this ice sheet are based below sea level. So this ice sheet is so thick and heavy that it's pressing down on the surface of the Earth. Much like when you go home tonight, you're going to sit down on your couch, you relax, right? So your body's like the ice sheet, right? And the couch goes down and it puffs up at the side, and that's exactly what's happening here. And so because this is underneath the water, right, this ocean water, as it warms, is effectively melting the underbelly of this ice sheet. And as it retreats, because it's heavy, you have this reverse slope gradient going down, right? So right now it's sitting on a little bump. There are no bumps to catch it for it to stop if it starts retreating. So once it goes past what we call this grounding line where it is right now, there's nothing to stop it from completely retreating backwards. And that's why we're so worried about these parts of the Antarctic ice sheet. And so the question is, well, when is that going to happen, right? That's a tipping point that we don't want to pass. I tend not to like this whole word tipping points, right? Because the problem with tipping points is that you don't really know where they are until you're past it. And you go, oh yeah, there it was, right? Because now it's changing really fast, right? It's a very difficult question to answer, like where are we relative to this tipping point? So here it is when it starts to retreat. Some of my colleagues who work on measuring this modern ice sheet have argued for many years now that they think we're actually past this tipping point. and that parts of the West Antarctic ice sheet have already retreated past their grounding line, and that this collapse is basically underway. Right? A few weeks ago, NASA released some data and images of a cavity beneath one of these ice shelves. I don't know if you saw that in the news, where that warm ocean water was eating away at it underneath, right? Which is another example of this happening. All right, so as you can see, the problem with these ice sheet dynamics is that once you cross something like that, it's not like you can decide, oh, okay, fine, we're going to stop, greenhouse gas emissions and make everything good now, right? We've already crossed that line. You can't reverse that process very easily, right? At least not for many thousands or maybe hundreds of thousands of years. This is a picture I wanted to put in. Some of my colleagues recently went about a month ago down to the Thwaites Glacier, which is part of the West Antarctic ice sheet. It's the first time that humans have ever actually laid eyes on this part of the ice sheet. It's thought to be the most unstable part of the West Antarctic ice sheet, right? So the National Science Foundation and NERC, which is a funding agency from the UK, have pooled their resources to bring researchers to this area so that we can better understand the dynamics of what's happening here, because this will really help us to project what's going to happen in the future. And there are a few penguins here in the foreground. You can make them out. Okay, so what did we learn from looking at kind of these ancient records of sea level rise? One is that the pathway that we set on kind of commits us to a certain future sea level, right? We may have already committed ourselves to something like 6 meters of sea level rise in the long term. What that means is that what you see today when you get flooding of your streets here, right, is really just the first step in what is going to be a very long journey of continual coastal retreat, right? It's not like we're just going to plan for, say, 2 feet of sea level rise and then it's going to stop. It's not going to stop. It's going to keep going, right, for quite a long time, just based on the amount of warming that we have already seen, right? The second thing is this issue about the nature of sea level rise. At some of the past time periods, we do see evidence for ice sheets collapsing or sectors of them going quickly. We don't yet know if that's something that will happen during one of these warm periods, and that's what we're trying to resolve by the work that we're currently doing in my research group. Okay. So another point I wanted to make here, which is related to this sea level commitment. I know you can't see this graph very well, but someone tweeted this out, I think a month ago. And I retweeted it, and I said, this is really not a joke. What the person wrote is that the next president gets to set the agenda for the next few tens of thousands of years in terms of temperature and sea level rise, right? Because what we do, even over the next year, 2 years, 3 years, 4 years, puts us on a pathway, right? And so we are committing ourselves based on the choices that we are making today. And that's a very important thing to remember. Okay, so let's move forward in time a little bit and look at something a little bit more recent and more on human timescales, right? Another thing we've been looking at are some tide gauge records, in fact, along the east coast of Florida and the east coast of the US. So there was a paper we published a few years ago that was featured in the New York Times that talked about how fast sea level had been rising in the southeast of the US, right? So this came out of a project I was doing with some of my colleagues at UF. One of them came to me with a tide gauge record near Cape Canaveral and said, I'm doing this study, and I thought I was looking at sea level to see if it could explain some of my data, and it looked like all of a sudden it started going really fast, and he showed it to me, and I said, oh, no, there must be something wrong. I'll sort this out for you, right? So I go to the NOAA website, I start downloading the data. Sure enough, he's right. I said, well, maybe something's wrong with that tide gauge. I'll go look at another one. And every one that I pulled between Miami and Cape Hatteras in North Carolina showed the same pattern, right? And it looks something like this. Here's the late 1990s, right? Going on until 2011 to 2015, there was this very rapid uptick in the rate of sea level rise, right? In some places, it increased almost by a factor of 10, right, at some of these tide gauges. And this was a pattern all across the southeast US. So we started looking into this because over this period of 5 years, we saw about 5 inches of sea level rise along this coastline, right? So for context, 3 millimeters a year, remember that number from before? 3 millimeters a year is equivalent to about 12 inches in a century. This is 5 inches in 5 years. No one's planning for that, right? This is the point in the conversation when I'm talking to coastal planners that their eyeballs start to pop out of their head, right? But it turns out when we look back in time over the last century at tide gauge records all along the East Coast, we can see evidence of short periods, kind of over several years, of these rapid accelerations in sea level rise. People call them hotspots, right? And it's an effect of El Nino and something in the Atlantic Ocean basin called the North Atlantic Oscillation, which is kind of similar to El Nino. And when the two of those combine in the right way, it piles up a lot of water along the east coast of the US. And then after a couple of years, it kind of goes away again. So you get these variations in the rate of sea level rise. So while sea level is going up, we're going to have accelerations and little decelerations, right? And anywhere along the east coast of the US, we might get something like 5 inches in 5 years. So that's something we need to be prepared for, right? We don't want to just look at these smooth curved projections when we're planning. We need to be prepared for the fact that we might get little bumps along the way. Okay, so these are some of the lessons that we've learned from looking at ancient sea level rise and recent sea level. And I've already talked about all these things. I've just written them out in words here. This last one that I talked about, though, we're still doing further work in this. Now we're looking at the Gulf Coast of Florida to see if that has a similar effect with these hotspots. And we're trying to see if we can understand, when they're going to happen. That would be awfully helpful for people planning, right? So that's an area of ongoing research that we are looking at right now. Okay, but when we go into coastal communities and talk with people, this is usually the graph that gets shown, right? Or something like this. You've probably seen something like this. These are projections of sea level. This is the past. So I showed you this part before, but now the scale has been expanded, so it's all squeezed down. That was that 1 to 2 millimeters a year of sea level rise. The little purple line is the satellite record that I showed you before, where it's up to 3 to 4 millimeters a year. And then, well, which way is it going to go? I hate showing this figure because you don't have to be a scientist to make a figure like this, right? It says, we don't know, right? It could be high, it could be low, it could be somewhere in between, right? Any one of you could have taken out your little colored pencils and drawn that for me, right? Well, the top line is based on a model, right, which we hope is the worst case scenario. That one does go up to 8 feet by the year 2100, which is an awful lot. And the reason it's so high is that if we start to melt those ice shelves at the surface and they start to collapse very quickly, then we'll get this kind of a bad positive feedback effect, it's called, where it will start retreating very quickly, like we talked about before. So that's our worst case scenario. But we might be somewhere in here. This one at the bottom is just a linear projection of that 3 millimeters a year. Personally, I think we should take that line off because we know it's not linear, it's accelerating, right? So we know it's going to be somewhere above there, but we don't know how much, and it really depends on the dynamics of this ice sheet retreat. So you look at something like this, and you throw your hands in the air. You say, well, what do we do with this information, right? I like to flip this on its head. When you look at these curves, there's an incredible amount of certainty, not uncertainty. We know that sea level is rising, and we know that it is accelerating. And that's really all we need to know to start planning for it, right? There's no excuse for any delay or inaction or focusing on uncertainty. I can't tell you how high sea level is going to be on December 13th in 2038. It's true. I also can't tell you exactly what day the next hurricane is going to hit, but I can tell you it's going to happen, right? And you're willing to prepare for it and build your houses in such a way that you're going to be ready for that hurricane, right? So we need to be ready for this, right? And it probably will happen a lot sooner than most of us think in terms of the magnitude of sea level rise. So while these are useful projections, it turns out I can guarantee you that sea level rise will not look like any one of these curves. It's very unusual for a scientist to use the words "I guarantee," right? The reason I can do that in this particular instance is because I know what sea level data looks like, and it does not look smooth like this. It looks like this, right? This is a tide gauge record from Virginia Key, which is down near Miami, and it goes from the year 1996 across to 2016. You can see it's messy, right? You can see there's an annual cycle to it, right? These are the king tides in the fall when the tides are naturally higher along this part of the coastline, right? So that's your annual cycle. You can see sharp peaks when you have hurricane storm surges come through. Here's Hurricane Irene, Hurricane Rita, Hurricane Wilma, Sandy, which did not make landfall, but there was a very large storm surge associated with that along this coastline. And then, boom. That's just a normal king tide. But it's at the same level as some of these hurricane storm surges because sea level has been creeping up in the background, right? That's the smooth curve part of it. And in fact, this was that part of the record I talked to you about before, 2011 to 2015, where it started accelerating very quickly. So we were having king tide levels at the same level as hurricane storm surges, right? So that's what the future of sea level rise is going to look like. We're going to have higher frequency, or in other words, more often, we're going to get these flooding events, right? And it may not be just once a year, twice a year, 5 times a year. And the question is, what is your tolerance for how many times a year can your property be flooded, right? If you're looking at the projection curves I showed you back here, so in Southeast Florida, they're planning for 2 feet in the year 2060, right? So they're somewhere on one of these blue, maybe the green curve, right? Somewhere on the green curve. It's going to hit 2 feet before it gets to 2060 with increasing frequency until it's there permanently, right? So I think this graph is actually very misleading because it makes it look like we're not going to get to 2 feet until we get to 2060 if we're on the green curve. But in fact, we are going to get there more and more often because that's what sea level data looks like. So I like to talk about sea level rise in terms of the frequency of coastal flooding rather than just using those smooth curve projections that you saw in the other diagram. The frequency of coastal flooding from high tides has doubled in the US in the last 30 years, right? In 2017, more than a quarter of tide gauge locations tied or broke their records for high tide flood days. And you can see the percent increase compared to the year 2000. This scale, if you can't read in the back, this is 250%, right? So these are huge changes that we've seen in the frequency of coastal flooding as sea level is rising, even though it's only 3 millimeters a year, which again doesn't sound impressive, but when you think about the effect it's having on our communities, we all know that it is very important. Okay, so that underscores this message that sea level rise will happen sooner than we think it will, right? Or than a lot of us do. So these are some of the key points that I've touched on throughout the talk. Things that we've learned from research that are kind of important for developing policy as we move forward. But to me, the real missing ingredient here in this picture, in terms of developing the policy, is how to motivate action at a level that we can keep pace with or hopefully stay ahead with the pace of sea level rise, right? The key is the motivation part. We know the research, we know the science, we can tell you with great certainty that sea level is going to keep rising for a very long time. What we need to do now is figure out good ways to implement this into effective policies as we move into the future. Another thing I want to point out to you, though, and I'm sure a lot of you are aware of at least some of these, but often when we think about sea level rise, we think about just whether or not it's going to flood our doorstep, right? And the flooding of infrastructure as being the main impact of sea level rise. And that's an important one, but it's not the only one. Right? I was talking to a friend of mine who lives in Coral Gables. He said, oh, we're good because our house is at 12 feet, so we will be fine, right? Well, their house might be fine, but if they can't get to work, or the sewage isn't working and they can't get fresh water, or maybe the nuclear reactor at Turkey Point stops working, you know, they might have some problems, right? So it's not just about your house, it's about all that infrastructure that you rely upon, right? One of those things is saltwater intrusion, right? Will you have access to fresh water as the saltwater is invading our freshwater aquifers? There are health issues that are associated with contaminated or standing floodwaters, right? During intense rainfall events, because sea level has risen, the rain has nowhere to go as it runs off the land anymore and it ponds up. This picture from Miami, where these roads are completely flooded, happened during a rainstorm. That was not a storm surge, right? There was no hurricane. It was just a rainstorm, right? And it can't flow off quickly enough because sea level has risen so high around that area, right? We get a loss of coastal resources through erosion. We have habitat loss, loss of infrastructure, and there's a very large social inequality to this, right? So as you all know, there are some communities that are taking action. They are raising roads, they are putting in pumps, they might be building seawalls because they have the money to do so, right? Well, then what happens to the people who don't? Where does that seawall end, right? If it's not going to rise there, it will rise even higher for the people who don't have this seawall, because that water has to go somewhere. So now you've made it worse for the other person, even though you're protecting yourself, right? There are economic impacts, obviously, right? As a state that very heavily relies on its coastal economy, and I'm a state employee, right? Tourism, real estate, coastal industries, right? All of these things are going to be affected. So this image, I got this today. I saw it this morning, and I wanted to put it into the talk. So here's a case in New Orleans where after Hurricane Katrina, they've decided to modify a lot of their levees and their infrastructure so that hopefully something like that won't happen again, right? So here's a report from the Army Corps of Engineers. After a $14 billion upgrade, right? They've just finished building these levees to protect New Orleans, but they're only 4 years away from becoming inadequate due to rising sea levels. $14 billion later, right? So very clearly, we need to be planning for the fact we know it's going to rise. We know that's going to happen. And if you assume a higher level, you will last for longer, right, is the basic answer. And again, I can't tell you exactly which day it will get to that level in Obali, but it is going to get there, right, is basically the answer to that. So the question is, how do we make our communities resilient? A lot of people have been pointing to this picture, which I'm sure many of you recognize. This picture comes from Mexico Beach after Hurricane Michael ripped through there last year. And this house comes from a guy, there's this whole story in the New York Times about it, right? There's this guy who built this house as a fortress. He said, I get it. I understand climate change is happening. Sea level rise is happening. I'm going to build my house, and it will stay, right? And it survived Hurricane Michael. Look, it's like the last one standing, right? Is this really the definition of resiliency, right? Because this guy doesn't have fresh water. He doesn't have sewage. He doesn't have neighbors anymore, right? I mean, so we cannot achieve resiliency on an individual level, is my message there, is that we have to build resiliency as a community, right? We are not going to be resilient unless our entire community is resilient as well. And that's a very important message to think about as we go further. So I spend a lot of my time talking about this, right? I do a lot of research, but I also do a lot of public outreach, like I'm doing here tonight, right? You want to go look at some of these things, I've been on Nova, at CNN, there's a TEDx talk out there that you can go and listen to. And the reason I do this is to share this message with people so that you can go out and talk to other people too, because again, we can't do this alone, right? We need to work together. We need to reach across to people maybe who aren't our friends to talk about how we're going to solve this problem. There's a map of Florida that I want to share with you, and it reflects public perceptions about global warming. So what this image is showing you is the estimated percent of adults who think that global warming is happening as of October 2018, right? And this color scale over here, the warm colors are more than 50%. It looks an awful lot like a political election map. You guys already knew that. I didn't need to tell you that, right? You saw that right away, right, when I put that up. But it turns out that a thermometer is not partisan, right? The scarf shows you the temperatures have been rising. The ice sheet really doesn't care how you vote, right? These are problems that we're going to need to tackle regardless of who we are, because they affect all of us together, right? In contrast to this chart here, where at least more than 50% across the whole state, and this whole Southeast, at least do think that global warming is happening. Let me compare that to this one. The estimated percent of adults who think that global warming will harm them personally. Oh yeah, it's happening, but it's not gonna affect me, right? I'm good, right? I have some money, I'll buy a seawall, or I'll sell my house at just the right time when, I don't know, who's gonna buy it then? I'm not exactly sure what they're thinking, right? So this is a real problem. And that's why you should buy a scarf, global warming stripes, go Google it, and show it to your neighbors, and talk about it. Because in fact, the most important thing that you can do personally is to talk about this problem with people. Because if we can't have a conversation about it, then we won't be able to adapt as we move forward if we can't even have a conversation about this issue, right? Okay, the last thought I'm going to leave you with is that this is the best summary of climate change that we can come up with. This is kind of a community thing that we use. Climate change in 10 words, right? People who understand all 5 of these points are much more likely to answer that, yes, they understand it and they think it's going to harm them personally, right? Firstly, it's real. We saw that with the scarf. Secondly, it's us, and I showed you the evidence for that earlier. 3, it's bad. That was the bad news part of the talk, right? We got out of the way early. 4, the experts agree, right? A lot of the media puts this stuff out that says that we disagree, we're arguing, we're debating it. We're not, right? Yes, we debate a lot of the details about things, but these fundamental things I've talked about tonight, we all agree upon. But 5 is the most important, right? And that's that there is hope. Like I said before, if the sun was moving rapidly towards the Earth or vice versa, it would be a real problem. But we actually know we have solutions at our fingertips. There are things that we can do. It's not like we have to invent new physics or technology to get ourselves to the moon, but you know what? We did that, right? We can do this too if we develop the social and political will to do so. So I'm going to leave you with this image of an octopus in a parking garage in Miami Beach. To me, this image is kind of the sea-level equivalent of a cartoon that probably many of you have seen. That's like the frog in the pot of boiling water, right? As you heat up that pot of boiling water, is the frog ever going to realize it's so hot it should jump out and not get boiled to death? At what point do we realize that this is just wrong, right? The ocean wants to be here, not the BMW, right? Thank you for your attention.
Hello.
Did we get the microphones around back there? No? Yes? So I'm sure Dr. Dutton would be willing to answer some questions, so I'm going to point at you, and you're going to talk very loud with your question. Yes?
Okay, so the question is, are there any estimations as to when the next ice age would be? People have made those projections, but it turns out that when you put in this amount of warming that we've already seen, that now we've basically escaped going into that next ice age, at least for many hundreds of thousands of years. And probably it would have happened fairly soon in a geologic sense in the next couple thousand years when you look at the records, right? So we have pushed ourselves out of that natural cycle that I showed you earlier.
Right there. Yes, you.
Okay, I went to school and I learned that carbon dioxide is heavier than air. I went to the surface and I got a helium balloon. It floats. I'd like for you to explain to me how you find carbon dioxide in the atmosphere when it's heavier than air.
Great question. Okay, that's because the atmosphere is well mixed and there's a lot of wind moving things around, right? So if you didn't have anything, it might all sink down, but it's being moved around, right? Our atmosphere, as you know, you experience with the weather all the time, is circulating all the time. You can actually look, NASA has some beautiful images online of what happens to the CO2 when it goes into the atmosphere and how it goes into these weather patterns, and that's what's moving it around.
Go ahead, stand up. Thank you. All right. Aim it at your mouth. Aim it right at your mouth.
Very good. So I'm curious about the pulses that we might experience, and in particular, I would like to know of one that I have heard about a potential pulse, and that is that there's a great deal of liquid water under the ice sheet in Antarctica, and I have heard the possibility that if it were to ever find an avenue out, that we would get what would amount to a very big pulse. Are you familiar with that?
Yeah,
And how much water are we talking about?
There are some lakes beneath the Antarctic ice sheet. We've actually drilled into one of them, Lake Vostok, right? And part of that ice sheet is melting at the base because of the geothermal heat that's actually being trapped there. So it's actually melting all the time in certain parts of the ice sheet. The bigger concern, though, is actually the ice. Because of the geometry of the bedrock that I showed you before, remember you sitting down on the couch, right? So because the ice sheet is pressing down on the land there, even if it melts, a lot of that water will be trapped in basically a big lake right there. And so it's only when that land starts to rebound from not having the ice sheet there that it will push that water out, and that will take thousands of years for it to happen.
Right here. Go ahead.
Is there much work done on the system dynamics of global warming and sea level rise, the impact it has on the Earth's rotation, on, I don't know, magnetic field?
Yes. So the question is there a lot of work done looking at climate change and sea level rise on other aspects of the Earth system, like the Earth's rotation, right? And that's a great question. When you melt an ice sheet, it does change the Earth's rotation. It changes our gravity field. So I actually work very closely with geophysical modelers who look at those aspects. So yeah, there are domino effects in kind of every direction. And those are things that are being explored both with models, but also by looking at data. There's questions on the left.
So what I'm thinking is, rather than fight this, since there's global warming and a lot of it should allow more arable land, for instance, further north, Canada, Siberia, wouldn't it make more sense to try to work with what's happening, especially since you said you don't know where the tipping point is, and rather than encourage people to stay in locations that could be dangerous, wouldn't it make more sense to right now start trying to get people to, like the Native American Indians, go with nature as opposed to trying to stay where you're at?
Yes, absolutely. So there are lots of ways that we can take advantage of this situation. We can even capitalize on it, like literally, financially, right? If we go in that direction, right? And that's exactly right. And one of the main points I often make in my talks is that the point of this is that we don't want to be building in the most vulnerable areas. We don't want to be purposefully doing things that we know are putting people in a vulnerable position. But that does mean we do need to change some of our ways, some of our current zoning laws, and we need to make those changes. And so the problem is kind of getting out of the status quo, right, and pushing in that direction. But I'm absolutely with you. Yes.
All right, insurance companies, especially flood insurance, they want to base their rates on probability. What type of information are they trying to glean from you folks?
Okay, so those projections of sea level, they do probabilistic projections of sea level that give certain percentages of what percent chance do we think each one of those curves is going to happen by a certain date. And those are the data that the insurance companies are using, right? Are those statistical results from the models that we're using. And it's not so much the insurance companies, it's the reinsurance companies that are really going to tip the scale when it happens. It's when they pull out and they stop subsidizing the insurance agencies, right, that there will be a big issue.
Which set of the data they're going to use, the top or the bottom?
Well, that's up to them, right? We can advise, but that's up to them.
In prehistoric times, what caused the decrease in atmospheric carbon dioxide?
Yes, so there were several things that happened to make those carbon dioxide changes. So one is that as it cooled off, you had the ice sheets, how much CO2 dissolves in water changes, right? So colder water will absorb more carbon dioxide, and as it warms up, it degasses more. It also changed the productivity in the surface of the oceans. So plants that grow, they draw down carbon dioxide. So it turns out there are actually several effects that added together to create those natural cycles that I showed you on that diagram. Great question.
The big bad wolf would seem to be CO2. Surely it is only at international level, the big industrial countries, that can move us into the hope area. What else can we do? We as individuals can do little bits and pieces, But if we are actually going to be hoping with any kind of reality in view, it has to be done by those people who create the biggest CO2.
It has to be done by all of us, right? So I agree. It needs to be both top-down and bottom-up, right, is my attitude, because we won't get to complete drawdown unless we're doing both things. If you want to know what you can do at an individual level, there are some resources that I can point out to you. One of them is called Project Drawdown that you can look up online. It talks about different things that you can do personally. There are obviously other things that you can do, like voting and talking to your representatives, becoming active in your community. As I said before, just talking to other people is something that we can all do together. But yes, the biggest changes do need to happen from the top-down level. But the quickest, but there are also other things that we can do quickly. For example, methane is a very strong greenhouse gas, and it's very short-lived in the atmosphere. So if we stop reducing methane, we will very quickly see a good effect from that, and a drop in temperature from that particular effect. Whereas carbon dioxide lives in the atmosphere for much longer. So even if we stop emitting as much CO2, it will take us a really long time to see the benefits of that. Whereas something short-lived like methane, we can see that very quickly. Yes.
Of the concerns you have about global warming, what percentage of concern is
So the question is, of the concerns I have about global warming, how much of it is concerned about melting frozen methane? Right, so in the permafrost, in the Arctic especially, there's a lot of methane that's trapped in the permafrost, and as it warms up, it's getting released into the atmosphere. And obviously, that will cause things to warm even more, and that process has already started to happen. Right, so we have, in fact, crossed that tipping point to some extent. So that's part of the story. It's part of my concern, right? But what will help with that is for us to reduce our emissions and reduce that temperature, and that's the way, that one can be reversed, right? More easily than something like the ice sheet that we were talking about before.
Shout it out.
Okay, I'll shout it out. I'm a tree person. That's my business, horticulture. And we have undiscriminating construction going on everywhere, where not only one or two trees are taken down, but swaths of whole areas of native plants and trees. Trees give off oxygen.
And they draw down carbon dioxide.
They take
Right.
carbon dioxide. So worldwide, we cut down trees every day.
Right, and one idea, one approach is reforestation, which can have a huge effect. People talk about, let's develop these technologies for drawing carbon dioxide out of the atmosphere. You know what? Nature's already done that for us. There's a really efficient one out there, and it's trees, right? Let's go out and plant trees, reforest areas. There are some countries that have done this very effectively, and it's making a big difference. So it's a very good point.
I'm from way upstate New York, but I'm here in the winter. This past year, what I have seen in 1 year, the trees that have come down to build up more malls, doesn't seem us who need any more
It's
malls.
devastating. I can tell you, every time we drive past the developments, my kids are in an uproar. Why did they cut down more trees? Because they listen to me all day long, right?
You
Using like,
can't dispute the temperature change, you can't dispute the sea level rise. I'm not a skeptic, but we are into astronomy. There's the lack of the sunspots, there's the changes in the axis of the Earth as well
Yes.
as the orbit changing relative to the sun. Have you taken that into account with your models?
Right, so the question was, have we taken into account some of the orbits of the Earth and those natural factors when we look at the modeling? So that was one of the things that was listed for that plot with natural factors. One of those is looking at the tilt of the Earth and the sunspots, and all of those factors add together to give us what's called solar insolation, which is the amount of sun's energy, and albedo too. So all of those things are included in the models, and over those short time scales, they have very little effect, right? Yeah.
Okay, one more, and then we're going to let Dr. Dutton get some rest because she flew in from California this morning.
Last night.
Last night.
I have two questions. It's two parts. What are the two main factors contributing to global warming? And if those two factors were cut by 75%, what would we see? Would we see any effect in the seawater or sea level change?
Right. What are the two biggest factors? I tell you, the one biggest factor is humans, right?
I mean, what?
That's my answer, and I'm sticking to it. No, well, so greenhouse gases are the big thing, right? And carbon dioxide by far is our biggest problem, right? So if you cut it by 75%, I don't know off the top of my head exactly which pathway that would get us on. But every little bit that we can cut makes a difference. So yes, the biggest countries need to be involved, they need to be at the table, but every increment does make a difference to make it better, and we shouldn't lose sight of that. And so your hope should not be passive, right? I'm not talking about passive hope, I'm going to sit back and hope. I'm talking about we need the courage to face this and to work together. Thank you all for coming out tonight. Thank you.